Today we are going to study XOR gates and their properties. We're talking about the nomenclature. The X comes from the word exclusive. Now, talking about the symbol, this is the symbol of a OR gate. Now, if we just add this becomes an XOR gate. Modified, it becomes an XOR. Now we can take two inputs, say A and B. Now it can be expressed as Y equals to A XOR B. Now, talking about the internal circuit, Y equals to A XOR B can be expanded like this: A and B complement, or A complement and B. Or we can also write it like A or B and A complement or B complement. We can easily implement this expression. So we just need two AND gates and they will have two inputs. Now starting that. It's namely A and this is B. Now for the second one I will use one NOT gate. Now this will act as the B complement. Now for the second one we will take A complement. So the output in this case will be A and B complement, and in this case it will be A complement and B. Now we only have to make an OR gate for them. And this can be written as Y equals to A and B complement, or A complement and B. Now we will make the truth table for the XOR, where Y equals to again A and B complement, or A complement and B. Now taking the values 0, 0, 0, 1, 1, 0, 1, 1. Now solving the first one, let's see what we get. When A equals to B and B equals to 0, it is 0 and B's complement will be 1, or A's complement now would be 1 and B. It is odd number of ones. See, here is odd number of ones, here is also odd number of ones. We get high outputs. Now also when we have even number of ones, we get low outputs. Now this property can be called as the odd ones detector. Moving on to enable and disable. We'll first make the truth table again. Now, as you can see in the input of A, when the input of A is 0, we get output Y equals to 0. When B is 0, we get output Y equals to 1 when B is also 1. So this can be called enable for XOR gate, acting as buffer. Now when A is 1, we get Y equals to 1 when B is 0, and we get Y equals to 0 when B is 1. So this is also enable for XOR, but this is inverter. Now because of 0 and 1 both being enabled for XOR, we call it control inverter, and let's see why. First we make an XOR gate. As we know, A is 0 in this case. Yes, B. This is Y. Now when B is 0, we get, when B is 1, we get 1. So we can say that Y is equal to B, and we can make this buffer, which is also equal to B. Now for the second case, A equals to 1, and we have B, Y equals to 2. So we see that when B is equals to 0, we get Y equals to 1, and B equals to 1, we get Y equals to 0. So Y is basically B complement. So we can make the invert not get here, y equals to B complement. Because of these things, we can call this a controlled inverter. And we say that Xor gate acts as a controlled inverter, as we can make it buffer or make it inverter just by changing the input from 0 to 1. Now let's talk about the properties. Number 1, A XOR A. Number 2, A XOR A complement. Number 3, A XOR 0. Number 4, A XOR 1. Now let's calculate here. We will use this expression. Now starting this thing. Taking the first case, when A XOR A, A and A complement or A complement is A, it becomes 0 or 0. Taking the second one, where we have to XOR A complement, we get A and A complement complement and A complement and A complement. We get A and A or A complement and A complement. We get A and A complement equals to 1. The third one, A XOR 0. Yes, A and 0's complement is 1. We all know that. Or A complement and 0 comes A. And about the fourth, it will be as A complement. We'll calculate it. Talking about the second property, if A XOR B equals to C, then B XOR C equals to A and A XOR C equals to B, then the main property here is A XOR B XOR C equals to 0. Now let's talk about the third property. If A XOR A equals to 0, we know that. Then what will be A XOR A XOR A? We know that A XOR A is equals to 0. That XOR with A, we get again A. So generalizing this, we get A XOR A XOR A n times equals to conditionally A when n equals to odd. equals to 0 when n equals to even. Now let's solve the problem here. There are XOR gates. Now we are cascading 20 XOR gates. Solving this, we can take this one is y1, this one is y2, this one is y3. y3. Now y1 equals to x XOR 1, we get x complement. Taking y2, we get x complement XOR 1, we get complement of x complement, get x. Also generalizing this, we can see that in even number of terms we get x, and in odd number of terms we get x complement. So we have to find out 20 XOR gates. So this will be y equals to x. That's it for today.